All right, welcome to our 17th lecture in this course on algebraic topology. I'm Norman Wahlberger at the University of New South Wales, and today we're going to talk about probably the central theorem in the subject, the classification of combinatorial surfaces. So the classification of surfaces is really at the heart of the subject, and what we're interested in is describing all the possible two-dimensional compact surfaces. So we've already seen things like the Klein bottle, the torus, an n-hole torus, the projective space, or the projective plane, and the sphere. We want to classify all possible two-dimensional compact surfaces. And by compact, we mean that the surface is first of all bounded, so it can be contained in a big box. It doesn't go off to infinity, and it's closed. It doesn't have any holes in it. And this very important problem was solved, well, it's essentially 19th century work. At the end of the 19th century, people started realizing what the list of compact surfaces was, but it was really around the first decade of the 20th century where it was completed. So I'm going to talk today about a traditional strategy. So the main strategy is to reduce to a combinatorial problem where instead of dealing with these sort of continuous things, we deal with something which is much more cut and dried or combinatorial, and we reduce to a standard form. So let me motivate that by having a look at how we reduce an arbitrary two-dimensional surface into polygonal pieces. So there's a two-dimensional surface. It might have a couple of holes in it and so on. And we imagine forming on the surface a pattern of polygons with vertices and edges. And these polygons are nicely situated with respect to each other so that they share an edge along a complete edge, just like this. Maybe they don't have to be planar, of course. They're covering the entire surface. So the idea is once we have such a thing, what we can do is we can cut the surface open and we can just display the various pieces that are the constituents together with the gluing relations that relate adjacent polygons. So we could take something like this and we could split it up into a pentagon there and a square over here and a triangle over here and then another that's another sort of quadrilateral there. And what we'd have to do is we'd have to be careful about labeling edges. So if we put some arrows and some labels, say A, B, C, D in some fashion or another, then we would have over here A, and B, and B, and D, say, and C, and C. And then these labels on these pieces would tell us how to glue the polygons together to get back the original surface. Now, if we think rather about this pattern of polygons, what are the essential features? So we have a finite set of polygons. with, oh, maybe we should say also what kinds of polygons. So polygons or n-gons, where n is, all right, well here we have triangular, quadrilateral, pentagonal pieces, but we could also possibly allow for two-dimensional, or two polygons with two sides. And so we can have 2, 3, 4, and so on. And perhaps we could even have polygons of one side. What would that be? Well, that would be something like a single edge like that. Okay? Or maybe we could have a polygon with two sides like this. Okay, why not? So we have a finite set of polygons, or n-gons, with edges labeled by letters and also directed. In other words, the edges have little arrows that tell us which way to glue two edges with the same label. And the crucial property is that every edge label occurs exactly twice. That's the property that will ensure that when we glue together, we're really getting something that's two-dimensional. So if there's an A appearing somewhere, there's got to be an A somewhere else in this polygonal pattern. And now we could actually make a definition. We could say that this structure is what we mean by a combinatorial surface. Okay? So this is what we might mean by a combinatorial surface. That's a finite set of polygons with edges labeled by letters, directed edges labeled by letters, with every letter appearing exactly twice. Now locally, these n-gons fit together to form a two-dimensional surface. And there's two things that we need to check there or just observe. One is that if we have an edge A from one polygon and we glue it to an edge also labeled A from another polygon, then any point on that common edge, say that one there, is going to have a neighborhood which is sort of a half disk from the one polygon and another half disk from the other polygon. And together those two half disks are going to form a little open circular neighborhood of a given point. So even though that we might be on the boundary of one of these edges, still, as far as the gluing is concerned, it looks like a two-dimensional surface near that point. Now there's something else to check, and that's what happens at a vertex. Okay. So at a vertex where several different edges meet, what's going to happen there is, here's our vertex, and we're going to have different edges meeting. So for example, maybe there's an edge A there, and an edge B there, edge E there, something like this. So this represents one corner of one polygonal piece, this represents another corner of another polygonal piece, and so on. And what's going to happen is that as we're looking at this vertex, let's call it capital A, as we walk around it, we're going to getting a segment from the first polygon, and then a segment from the second polygon, and we're going to keep on going, and all of the edges that come together here are going to form a cyclical pattern until we get back to the original one. Because the edges all come in pairs, so we're starting with an edge A, then an edge B, and so on, and eventually we have to get back to that edge A again, and so eventually that will close up and we'll have a bunch of circular arcs coming together to form also a circular disk near the vertex A. So at a vertex, we get a cyclic pattern of sort of wedges that form also a little open disk neighborhood. All right, so here's an example of how we can create a surface abstractly in this way. So let's create a surface M by having a bunch of polygons, say A, B, C, D, and then a triangle, G, D, E, and a two-gon, edge A and G, and a pentagonal one, edges C, E, B, F, and F. So is it a combinatorial surface? Well, it's certainly made out of polygons. There are two A edges. There are two B edges. There's two C edges, D and a D. There's two D edges, two E edges, two F edges, and two G edges. So the edges all appear in pairs. So this is a combinatorial surface. Well, what do we get when we sort of glue them together? Well, let's have a look at the vertices here. Let me illustrate what I was talking about with the way the vertices fit together by let's having a look at this vertex right here. Let's call it A for a second. And suppose that we think of this vertex starting from here, and we're, let's say, moving in this direction here along this polygon. So we start from the top of edge D, and we end up at the bottom of edge A. And so if we keep going this direction, then the next place where we're going to be is at the bottom of the other edge A, which is, here's the other edge A, and here's its bottom. And so we're going to be moving in this direction here. So this point here has got to be identified with this point because this edge A is identified with this edge A. It's glued together. So this point has got to be the same as that point. So we've also got to label that vertex as A. Okay, so we're making our little tour around A. We've just gone around here, and now we're here, and we're going along here until we get to this point right here, which is at the top of the G edge. And so that's going to be glued to, we look for the other G edge, here's the other G edge. That's the top of the G edge, and so we're going to have to move now in this direction. That means that this vertex here is also the vertex A. So following along, going around A, we're going around here, and then we're going around here, and now we're going around here, and we can carry on. At the top of D, we have to attach to the top of D. Oh, that's actually right there. So now we're back to where we started, and that's a closed loop around the vertex A. That piece, that piece, that piece, we're now back to where we started. Let's choose a different vertex, say this one here, B, and let's go around it. Let's go around in this direction. So starting at the top of A and then moving to the bottom of the edge B. There's the bottom of the edge B over here, so we're going to be now moving in this direction. And that point there has also got to be the vertex B. It's going to be glued to this one because the edge B is glued to this edge B. Of course, you may have to take this polygon and flip it over to do that, but that's all right. Okay, now as we carry on, we're moving here, and we're now at the top of edge E. And the top of edge E is over here. So now we're going to carry on like this. That must be also vertex B. Now we're at the bottom of D. The bottom of D is over here, so we're going to go carry on like here. That must also be edge B. To the top of C, right? To the top of C is over here. So now we're going this way. That must be edge B, vertex B rather. To the bottom of E, bottom of E. To the bottom of G. Bottom of G was over here. Now we go this way. To the top of A, and that's where we started. Okay, so that's now a complete traversing around the edge, around the vertex B. Have we accounted for all the vertices? Well, not quite. There's still, for example, this one here. Let's call it C. All right, let's carry on with that one. Same kind of thing. Let me go, say with yellow. So we're going to go initially around that segment to the bottom of C. Bottom of C. Where is C? Here's the C. The bottom of C is this, so we're now going in this direction. That must also be the vertex C. To the top of F. Well, there's the other F, and so the top of F is this one, so we must be going like this. And now we're at the bottom of F, so which is over here, so this must also be the vertex C, and now we're going in this direction. To the top of B, and that's where we started, to the top of B. So that was a little route around the vertex C. And so we've now accounted for all the vertices of our polygons. They've all been labeled. And if we glue this together, if we're able to glue this together, we can make an Euler number calculation now, because we know how many vertices, edges, and faces there are going to be. So the Euler number of this surface is going to be the number of vertices minus the number of edges plus the number of faces. We've just seen that there are actually going to be 3 vertices because we've counted them. They're capital A, capital B, capital C. How many edges are there? Well, there was A, B, C, D, E, F, G, 7 of them. How many faces? Well, that's just the number of polygons, 4. And so we get an Euler number of 0. This surface, whatever it is, must have Euler number 0. What are the possibilities for a surface of Euler number 0? Well, I remind you that if we have a torus, which we might write A, B, like this, that's a torus. We can actually calculate its Euler number directly from here also. These vertices are all the same. They're all glued together. There's 1 vertex, there's 2 edges, and there's 1 face, so its Euler number is also 0. But there was another possibility. There was also the Klein-Bottle that we get by going A, B, and then A in this direction and B like that. That's the Klein-Bottle. And a similar kind of analysis. Chi equals 1 minus 2 plus 1 equals 0. So that also had the Euler characteristic 0. So just knowing its Euler characteristic is not enough. It still could be either one of these 2 surfaces, or maybe it could be some other surface that we don't know about. Okay. But can we at least determine whether, if it's one of these, which one it's going to be? Well, the difference between these 2 surfaces is that one is orientable and the other one is not. So we can look at this thing here and say, well, can we figure out whether this is orientable or not? And we can. there is some special feature about this that makes it reasonably clear that this is not orientable. And what's that special feature? It's the presence of these two F's right here. Okay? This is an F in this direction and an F in this direction. That's a lot like another important surface that we talked about, the projective plane, which had a story like this, F, F. Remember we were gluing opposite sides together? So if you take a right-handed person and you walk them through this F here and then march them up through the corresponding other edge, then you'll see that the orientation reverses. So these two edges being here like this means that we're essentially in a similar situation. So this thing here is going to be non-orientable, whatever it is. So it's possibly the Klein bottle, or maybe it's some other thing which we don't know about yet.
So is that saying if we can find a Mobius band in it, then it must be non-orientable?
Yes, if you can find a Mobius band in it, then it's non-orientable. So whenever you can find a non-orientable surface within a surface, the bigger surface has to be non-orientable as well, because the little part is non-orientable. Now, before I leave this example, let's observe that this combinatorial way of representing the surface, whatever it is, allows us actually a very efficient algebraic representation of what's going on. Because we can encode these polygons by essentially encoding the series of edges that we go around as we go around the polygon. So this polygon here, we could represent it by a word that we get by going around the polygon. Okay, well, we could go around either this way or this way. It doesn't really matter. Let's go around this way because maybe it's the usual positive direction. Okay, so if we go around this way, then no, actually, let's go around this way because they all happen to be in this direction. So I'll go around this way. So edge A, and then edge B, and then edge C, and then edge D. So this word encodes that information. What about this one here? Well, if we go in this direction, so edge G, but now we're going along the edge D in the opposite direction, so we could encode that by putting a D inverse there. D inverse because we're going against the direction of D, and then we're going against the direction of E, so we could record that by an E inverse. So that little word encodes that triangle. What about this one? Well, this would be, say, A inverse, G inverse. And what about this pentagon? That might be C, E, B, F, F. And so the whole polygonal combinatorial surface could be represented by essentially just combining these words. So the combinatorial surface, M, is represented by the expression A, B, C, D. Well, let's just use plus G, D, D inverse, E inverse, plus A inverse, G inverse, plus C, E, B, F, F. But this is non-unique. We've made various choices. First of all, we've chosen which order to list the polygons. It clearly doesn't matter what order we list it, so we can sort of commute these words, right? So, for example, we could commute these words. We could write G, D inverse, E inverse first, and then A, B, C, D. But something else that we could do is we could, instead of going around, I went around this way to label things. I could also go around this way. Going around this way would just represent taking the polygon up, flipping it over on the other side. It's not changing its polygonal nature. So what would happen if I went in the other direction? Well, in that case, I'd be going, instead of going this way, I'd be going this way. So I could write GA. And say with this one here, instead of starting at the edge C, I could have started with the edge E. I could have said, let's write it EBFFC. EBFFC. So this represents a number of different ways that we have of rethinking about what the combinatorial surface is. We can first of all rearrange the words. We can flip any word around or sort of invert it. So for example, A, B, C, D, if we were going to invert that, that would be like D inverse, C inverse, B inverse, A inverse. And if we went around this one here in this direction, we'd have to go A, opposite A, and then opposite, oh, sorry, let's start with D. D inverse, C inverse, B inverse, A inverse. And those of you who have taken some group theory recognize like this is like how you take the inverse in a group. Okay? So you have to change the order as well as changing the inverses. So that's one kind of transformation that we can do. And the other kind of transformation that we did was something like EBFFC. We can rewrite that as, but it's just starting in a different spot. So just sort of moving the front to the back, BFFCE. We're doing that more over. So this actually raises an interesting possibility. It raises the interesting possibility that we could define what a surface is, purely algebraically. Right. So there's a natural question sort of floating around behind here is, what exactly is a two-dimensional surface? Okay. And that's not at all so clear what the answer to that question is, in fact. Right. And now we see that one way of getting at that is to say, well, a two-dimensional surface is really a word or an expression created with symbols with certain rules that allow us to change the expressions, namely these kinds of rules. So the question is, what is a surface? Could be answered. So a possible answer is a certain expression in words with letters A, B, A inverse, B inverse, and so on. According with certain conditions, like each letter has to appear twice, and we have certain notions of equality. Okay, so now let's have a look at how the proof of this main theorem goes. Well, what is the main theorem? And I want to sketch a traditional proof of this main theorem and also a more modern proof called the zip proof. So here's the main theorem. Classification of connected combinatorial surfaces. So every connected combinatorial surface can be represented in exactly one of the following standard forms. So the first is the case of a sphere. And a sphere has representation A inverse. Okay. That's the case where we have an A like this and an A like this. So if you think of that polygonal surface, and you remember if we glue those edges together, then you have to glue this to this, this to this, and that's going to form a sphere. So that's a polygonal or combinatorial representation of a sphere. That's our basic, most simple surface, so that's certainly one possibility. Another possibility is, well, a sum of tori, plural of torus, sum of tori, or an n-hold torus. And that's the case when we have M is, the word for M can be written as A, B, A inverse, B inverse. And maybe I'll put subscripts A1, B1, A1 inverse, B1 inverse. Then followed by A2, B2, A2 inverse, B2 inverse. And keeping on going till we get to AN, BN, AN inverse, BN inverse. So, well, of course, this one here is a sphere. That's its picture. Here, the picture is a torus with n holes. And combinatorially, in terms of a polygon, that's its representation. Or the third possibility is a sum of projective planes or cross caps. And that's the case when we can write M as, let's say, A1, A1, A2, A2, up to A, K, A, K. So a special case, if we just have a single A followed by A, then that's our projective plane. AA is the projective plane. If we have more than just two edges in the same direction, then that's called a sum of projective planes, and that's another possibility. So the theorem is that every combinatorial surface is exactly reducible to one of these three standard forms. And moreover, M is then determined by its Euler number together with its orientability. In other words, if you know the Euler number and the orientability, then you know exactly where it is on this list. So maybe I might make a table here. So chi equals 2. That's our sphere. Maybe I'll do a this is the orientable. This is non-orientable. So chi equals 2, we have the sphere, so that's got its word is A inverse. That's our sphere. Chi equals 1. We have A, that's our projective plane. For chi equals 0, there are two possibilities. One is A inverse, B inverse. That's a torus. Another possibility is A, B, which is a sort of another form for the Klein bottle. Beg your pardon?
Is that like the Riemann surface?
No, it's just a Klein bottle. It's just the same as the Klein bottle that I had over here. It's just a different representation of it. But it's exactly the same as the Klein bottle surface. Chi equals minus 1. Well, there we could have A, B, C. That's 3 different cross caps. Chi equals minus 2. It could be A inverse, B inverse, C inverse, D inverse, which is a 2-hole torus. Or it could be A, B, C, D. 4 cross caps. 3 cross caps. 4 cross caps. At chi equals minus 3. There's no orientable one, but if we just add another cross cap, A, B, C, D, E, 5 cross caps. So maybe I'll just write down what the Euler characteristics are for in these 3 cases. So for the Euler characteristic of the sphere, we have chi equals 2. For an n-hole torus, we have the Euler characteristic is 2 minus 2n. And for the sum of, I'll say, k projective planes, or cross caps, we have the Euler characteristic is 2 minus k. Okay, so that's our main theorem. That theorem was probably stated first very clearly in this form around 1910, well, probably exactly 100 years ago, roughly, by Dane and Heegard. Okay, so I'm going to give you a traditional proof, and then we're going to have a look at another proof a little bit later. All right, so we'll look at the details of the proof in the next lecture, but let me just give you the idea of the proof first, or the outline, so we know where we're going to go. This is perhaps one of the first real proofs that undergraduates can meet, where there's actually an argument. The argument is not that hard. Every step is reasonably coherent and logical, but we have to go through a certain number of steps and have to look at it carefully. And it's rather interesting and very pleasant, I think. So the idea is we're going to have a series of reductions to this normal form. Okay, and our basic strategy for reducing is cut and paste. And what does that mean? Well, it means that we're going to allow ourselves to do the following thing. Suppose that we have a piece or a polygon, and in fact it'll generally be a lot bigger, but suppose we have something like A, B, G, H, or H, L, just for the sake of argument. Okay. Then we're going to allow ourselves to replace this by making a cut. Okay. So we're going to make a cut, and we're going to label that cut with something, let's say C. And then we're going to replace that original polygon with two new polygons, just what we get by making that cut. So B, G, H, now C, together with this other piece that we've cut off, A, L, C. And we're not just going to go in this direction, but we're also, of course, going to go backwards. So if we have two pieces like this and we have a common edge C, then we're going to allow ourselves to glue those two pieces to go from here to here. Okay. And we're going to do that in a judicious way to simplify the original thing and to get it into one of these standard forms. And I guess another important thing that we're going to do is we're also going to reduce. We're going to reduce the edges in a certain situation when we have the following picture. Suppose that we get to the situation where we have something like this, where there's an edge A here and another edge A inverse, essentially, but A in the opposite direction, and some other stuff, B, let's say D, F, K, let's say. So the crucial thing is that we have, if we're going around here, if we look at the word, say we're reading in this direction, we have an A inverse, and then B, K, F inverse, D, I suppose. Okay. We have an A followed by an A inverse. Now, if this was group theory, the A and the A inverse should cancel. And that's also what we want to do in this case. Okay, so how are we going to cancel these two A's? We're going to just think about replacing this one with a slightly modified one. Just perhaps it's easier if I redraw it. So there's the A, and now there's the A coming in. There's still B, K, F, and D. So I've just pushed this vertex in a little bit. And now we're just going to glue these two edges. After all, these are gluing instructions. So we're going to glue these two edges together. And then that will give us B, K, F, and D. So now there'll be a B running this way, our K here, our F in this direction, and D in this direction. And the original vertex A has sort of been absorbed in the middle there. That was what used to be the edge A. It's now been glued together. So the word of this would just be B, K, F inverse D. Just what you get from taking this word and just getting rid of the A and A inverse. Okay, so our strategy is going to be the following, our steps. So step one is we're going to glue all the polygons together to form a big polygon. We started with many little individual polygons with these edges opposite, and whenever we have one polygon, we just look for one of its edges, a free edge, and say K, and then we look for the other polygon that has a K, and we just glue the two things together along the edge K. Now we have a bigger thing. Then we look at one of those free edges and look for another polygon that we haven't used yet and glue it together. We're not folding any existing polygons onto themselves. We're just taking ones that we haven't attached yet and attaching them. Okay? So at the end of that process, we have all of our constituents arranged in some big polygon with lots of edges, each edge appearing twice. Then our second step is to modify that so that there's only one vertex. So in other words, if we looked at one of these vertices, let's call it A, and we went around here like I did in that first example, went around there, I might find another edge A, and then I might find another edge A, and then I might find I'm back to where I started. So that would be one vertex, and then I would do the same thing for another vertex B. Okay? I don't want that situation. I want where, there's only one vertex around the whole boundary. Instead of having A, B, C, and so, I want to modify it so there's only one vertex. Okay, so it's possible to do that. That's a step. Okay. So after we've done that, we will have step 3 is we're going to distinguish between two types of edges, between edges which are in the same direction and ones which are in the opposite direction. So we get a normal form for same direction edges. Well, that means, okay, there's an edge A like this, and then some other stuff, and then there's another edge A, something like that. We call these edges are in the same direction. That when we read the word, there's an A that appears, and then eventually the A appears also not with an inverse. Okay. So we want to go from this kind of situation to a situation where the two A's have been replaced by, say, A primes, which are together. So we want to replace this with, say, a new edge A prime and a new edge A prime, which are together. Okay. And then we're going to have a look at the opposite direction edges. Step 4, so to get a normal form for opposite direction edges. In other words, we're going to look for situations where we have an edge A, and then over here, the other A that appears is in the opposite direction. So there's a situation where we have a letter A appearing and another A inverse appearing. And what we want to do is we want to replace this kind of situation with something where we have something of the form, say, A prime, B prime, A prime inverse, B prime inverse, and some other stuff. So this will be our basic ingredient for the projective planes, the sum of projective planes or sum of crosscaps. And this combination A, B, A inverse, B inverse, that's appearing in the sum of tori. Okay. And then there's a fifth step, step 5, which is kind of a trick, which allows us to combine a cross-cap plus a torus, or sometimes called a handle, to 3 cross-caps. And then with that, we'll be able to put every surface in its proper place. All right, so that's what we're going to do next time. We're going to have a look at this proof in some detail and try to understand exactly how we get every combinatorial surface into this standard form. See you then.